Next one is pasevals theorem. If this already known to you, relevant to the law of conservation of energy. That means we know if anything going to be transformed from one domain to the another domain, the energy may not be destroyed. That will be converted from one form to the another form. Simple example, if you are working in a Fourier transform, the energy in a time domain will be equivalent to the energy in a frequency domain. That means samples, energy spanned among all samples will be equivalent to energy spanned in the spectral components or spectral samples. Like that, here in a wavelet transforms, we are going to transform the time domain signal to the wavelet domain. If the scaling functions and wavelet functions form an orthonormal basis, there is a Parseval theorem that relates the energy of the signal g of t to the energy in each of the component and their wavelet coefficients. That means it will relevant to the energy distribution in a wavelet domain. So already you know C coefficients will indicate that scaling coefficients, D coefficients will indicate that wavelet coefficients. Then total energy distributed by g of t will be equivalent to energy distributed among scaling coefficients to the energy distributed among wavelet coefficient. That is the Parseval's theorem. How the energy will be distributed among all the coefficients in a wavelet domain is going to be given by the Parseval theorem. Then WT shows that it is possible for the scaling function and wavelets to have compact support. That means already we discussed that to be orthonormal. If we choose our scaling functions to have compact support over 0 to 1, then a solution to this expression is a scaling function, that is a simple rectangular function. Solution for this. Already you have some idea about scaling function representation in terms of coefficients and translations. We'll stop here.